During this presentation, keep this claim in mind. The center of gravity of a 2D object, assuming uniform density, is the point with an equal distribution of area around it. We're going to use the polygon tool to construct our square so that all the vertices can be manipulated later. So we're not going to use the normal square diagonal intersection or the midpoint of a diagonal or the connection of the midpoints of the sides to find this center of mass. Instead, we're going to use the method that you would normally use for a general quadrilateral. And that method is to find the centroids of each triangle created when you cut this square with diagonals. So this is going to look kind of strange. So let's find the intersections. And these will be the centroids of those triangles. Now we connect them with segments. And the intersection of these segments is the centroid of the quadrilateral. And notice how it falls right on 0, 0, exactly where we wanted it. Now we're going to hide some objects. Most of them, in fact. For easier viewing. We're going to leave a few of them. Just those. Okay. So now we're going to cut this quadrilateral into triangles to better show what we need to show. So what we're going to try to show is that when this shape is manipulated to where it's similar to a triangle, it's still going to be the centroid. And that's going to show more that this will be the centroid of any quadrilateral that's irregular. That's the first step. So first we're going to also sum the areas of each alternating triangle, or these corners sum together, this sum together, and these sum together are all going to be the same, obviously right now, but even when we change the shape, they will remain the same. So obviously these right now in the shape of a square are going to be the same. But we'll show when the shape is changed, they will remain the same. So as you can see, that would be the centroid of a triangle, a right triangle right there. And as we get closer and closer, where those lines cross, the intersection would be it. As we get closer and closer to a right triangle shape, our centroid approaches that point. So now we're going to test a obtuse triangle, and we get closer to that, and it approaches that point as well. No matter where we move this, as long as it's close to the triangle, it's right there. So now we're going to try to make an acute triangle. And as you can see, it still remains there. This is a quadrilateral now. This is not a triangle. It's an irregular or a general quadrilateral shape. So now we're going to test we can probably hide those now. But now we're going to test a rectangular shape. And keep noticing how all these areas remain the same. This rectangular shape, well, every section is the same. So obviously that holds true there. Now we're going to test a parallelogram. Yes, every area is the same. And these are all equally distributed around our centroid. So now we're going to test some more strange shapes. See how those areas remain the same over there on the left. It doesn't matter where I move this. And as I move it in, though the areas towards the point seem to get smaller, the other areas on the left, top left and bottom right get smaller as well. And this area summed with this area is equal to this area summed with this area, and this area summed with this area, and this area summed with this area. So this shape remains, the centroid remains the centroid all throughout these movements. It doesn't matter where you move anything, the area is still equally distributed around this point. So that's the proof. Thank you.